Right, so now we begin triple integrals. We start this off in Cartesian coordinates, um, and shortly we'll see what to do in cylindrical and spherical. But here we are. In this entire section, we're working in in Cartesian coordinates. So the first thing that we have is this Fubini's theorem, which says that a triple integral where it's not specified the integration order can be written in basically any integration order. So in this instance, you have dx first, followed by dy, followed by dz. This is assuming you're integrating over a rectangular box like this. So you see that the x-coordinate ranges from a to b, the y-coordinate range from c to d, z-coordinate range from e to f. Basically, this equality is true um, predicated on assumptions of the function being nice, and in particular that the function is continuous. So once you have that, then yeah, this triple integral is equal to this nested iterated integral. And as the statement says here, this is true for any of the other orderings that you can have. So you have a total of 6 possible orderings for this nested triple integral, since it's 3 times 2 times 1, 3 factorial, which is 6. Okay. Now, just as a rather straightforward example of showing how you calculate a triple integral, well, it's the same as you would do for a double integral. You just start on the inside and you work your way out. That is assuming that you don't have any of the nice properties of the function or the limits of integration that allow you to split it apart. If you don't have that, then what you may as well do is to just go through it from inside out. So here you see that the first thing that I do is I integrate with respect to x, resolving the inner most integral. So then we're supposed to evaluate this at x is equal to minus 1 and 5, which when you end up doing that, and I believe you have to simplify a little bit to get it in this format, you end up with this function. Next, you handle the next innermost integral, which is going to be the integral with respect to y. So we integrate with respect to y. I think that's pretty clear how we do that. Then you have to evaluate at y equals 2 and y equals 4. Simplifying the evaluation gives you this. Then lastly, you integrate with respect to x, or z, which is also pretty easy to do. It's a polynomial. Evaluating at 0 and 1 gives you the final answer. Okay. The next example that we have, it gives us the function without any integration order, and it gives us this as the domain that we want to integrate over. So that's what our B is. Our B is a box in Cartesian coordinates. So you can see that the bounds for x, y, and z are all numbers, right? Rather than being functions of each other, they're just numbers, which means that it's a box, a rectangular box. So that's convenient for setting up the next part, which says to use this particular integration order to integrate with respect to z, then x, then y. So I try to model this problem more similar to your homework problem that I think also specifies a specific integration order. So what you can do is, because this is the bounds describe a rectangular box, you don't have to modify any of the bounds to get the functions in one particular way. Since it's just a box, you can actually just copy down the bounds from the box directly. So we're told to do it in the order dz, dx, dy. That is what I would first put when I write things down. And then the integrals I would put next. Well, maybe I'd put the integrals signs themselves down, but I wouldn't know what the bounds are without sort of corresponding them to the actual integration order. So because we're told to do it with respect to z first, then my innermost integral has the bounds that are based around the limits for z. Next, we're supposed to do it with respect to x. Well, the next guy is this one, and the bounds are taken from the bounds for x. And then for y, again, it's the bounds for y. So this is particularly nice to do when your domain you're integrating over is simply a rectangular box like this. If it's all just numbers, then you don't need to think at all. Well, you don't need to think too much about inserting the bounds. You just have to make them match up. I think there's an example where it's slightly more complicated, where you do need to actually fiddle with it to get the order correctly. But basically, if these were functions, say like if the bounds for y was a function of x, and you wanted y to be on the outside, like the way it is here, you'd have to basically rewrite the bounds to make it so that instead x depends on y. You can kind of think about that visually sometimes, but we don't have that here. So let's come back to this. So integrating with respect to z, that's not too bad. The x squared y is treated as a constant. You can pull that out. The z is the only thing that gets integrated. So you end up integrating z. That gives you z squared over 2. You would evaluate from 1 to 5, like so. Doing the evaluation finally gives you this. Next, you're supposed to integrate with respect to x, so that will be an x cubed over 3, but the division by 3 will cancel with 12, so you get 4x cubed times y. Y, again, is treated as constant with respect to this integration. Okay, then you evaluate at x equals minus 2 and at 1. Simplifying gives you this, and lastly, we integrate with respect to y. We handle the outermost integral. And so, yeah, we end up with this answer. And just as a remark, if we weren't told to use a specific integration order for this problem, right, where you have x squared times y times z, and you have a rectangular box, the easiest way to do this would probably be to split this into a product of 3 different integrals, right? Because this is a product of 3 different functions, and because our domain doesn't have any dependency between the x, y, and z, the way that the x, y, and z ranges. And so you can actually very quickly set it up like this. You'll notice that the x goes from minus 2 to 1, which is exactly here. The y goes from 0 to 3, which is exactly there. And z goes from 1 to 5, which is right there. So then you could integrate each of these individually, evaluate them, take the product of them, and you end up with the same answer. So this would most likely be how I would do this integral if I wasn't told a particular integration order. I would resort to this. Okay. Right, so now we start introducing this kind of slight dependency that can happen between variables. Okay, so before we were only talking about integrating over a box in Cartesian. Now we are still in Cartesian, but we have this kind of dependency showing up. Notice that the bounds for z depend. They are functions of x and y. And this picture kind of illustrates this, although it doesn't illustrate it that well, because really what you would want is that like this surface that is being labeled by E, like this could be some thing where the height actually changes, whereas in this picture it looks flat. So instead, think of it as something which can vary depending on where you are in the xy plane. It is also showing that projected down the xy plane, this looks like some kind of an ellipse, or perhaps it's a circle, but just really distorted. So the idea is that in one of the projections onto the coordinate plane, you have something that is describable as a way that you integrate over. And then you end up having this final, this innermost integral, which in this case is the integral with respect to z, that ends up depending on the 2 outer variables, the x and the y. Right? So because z depends on x and y, the z integral needs to be inside of the x and y integrals because it depends on the values of x and y. And you can kind of see that in this theorem that I've written. So the description for E is the same. Z depends on x and y. And again, we're assuming that the function is continuous. Just niceness properties of the function so that all of the desired properties hold. So this triple integral, so you can see that this is kind of this is like a Fubini's theorem, right? Where this triple integral that is not specified in how you integrate over it, but it just says integrate over this entire solid E. Well, the way you can do it is that you would have a double integral over D, right? So it sweeps out over this two-dimensional region D that lives in the xy plane. And then for each point in the xy plane, for each point in D, what you do is you do this inner integral. You integrate for this specific point, this x comma y. You integrate from u1 to u2 of that point, which is basically a vertical slice along E. Right? So maybe I can graphically depict what that is saying. So it's like once you've picked a point here, once you sweep over the xy plane, you end up for every individual point in that integral that is being swept over this domain D, you then you're then going to map it into E using U1 and U2. So when you hit it with U1, you would end up, say, at this point. You hit it with U2, you end up at this point. Both of these points will project down to this one point at the base. And then when you integrate over it, it's going to be a straight line that connects these two. That is what the third integral, the z integral, is going to range over. Right? The u1 or the x and y have been fixed, and then you have to range over z. And then as you do that, you end up summing up the values that the function f takes at this triple of coordinates, or this over this coordinate. So that is what's going on here. And then of course you do that over every point in the domain D. So you then sweep this line over every point that you could change the base to being, right? And you can visualize that, yes, this is going to sweep out over the entire solid E. And that's how such a triple integral works. And I'm making a comment here that it wasn't important that we started with it wasn't important that the domain was represented easily in the xy plane and that z was sandwiched between functions of x and y. You can have similar versions of this where you more easily project onto the xz plane or the yz plane, and where the functions where y depends on x and z, or where x depends on y and z. So these are just this, but where the solid E has been rotated to match the description. So like if I were to rotate E in clockwise 90 degrees, I would end up with the same picture, but whereas D will be projected onto the XZ plane, and that will give me this kind of situation. So it's basically just rotations of this kind of image that are these things. Okay. And I believe we have some example that works with this kind of problem. Right, so if I remember correctly, this just involves quite a bit of algebra. So you have a function here. I believe I made this function match up with your homework problem. And the domain, I've also kind of made it similar. So you can see that x and z, the bounds for them are numerical. They're just numbers. So we only have the dependency show up with respect to y. And it didn't have to be that this was 0. I could have made the problem a bit worse and made this a function of x. But here I've just made it so the evaluation is slightly simpler. So you can see that because y depends on x like this, what this region forces in our integration order is it forces us to put the dy inside. right? Because, well, at least it makes the dy need to be inside the dx, so that we can think of it as like um, we have to fix the x before we sweep out the y. And so you can see that it does hold true in the order that I've written, but there are I think three orders that you could write where the integration with respect to y is inside the integration with respect to x, and I've just chosen one of them. I think the grabbing the bounds um, from e should be pretty clear. You just sort of make them match, right? So x ranges from 0 to 2, which it's said to do. Z ranges from 0 to 1, and then y ranges from 0 to this 2x minus 3. You could have written the dy outside of the dz, like you could have put dz as the innermost guy. That would have been acceptable. You could have also pushed I think, the dx into the dz, making the z integral the outermost guy. That would also have been a correct order. So what I'm saying is that the other orders that are possible, uh, 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 the orders dy, dx, dz, and dz, dy, dx also work, right? If you wanted to get the dy outside of the dx, then what you need to do is think about how this relationship depends on how the y and the x depend on each other. Which what you could do is you could sketch it and notice that this should be some kind of a triangular shape. I didn't actually bother to try this out, but we can look at it now. So at 0, it's at minus 3. Minus 3. So when x is equal to 0, you can see that y goes from, well, 0 to minus 3. So maybe that's not a good... yeah, the way that it's written, I probably wouldn't include that. Alright, so when is this equal to 0? At 3 over 2. Um, hmm. I'm just gonna assume that it's fine to actually have the order be reversed. It just means that the integral will end up being negative, and you'll um, have opposite sign. So really, this when you plug in at 2, you end up with 1. So this is supposed to be a triangle. So what you'd have to do if you wanted to switch the order with respect the order between x and y is you'd have to rewrite the bounds. So you can see that y ranges from minus 3 to 1, and that z would have to go from 0 to whatever, however you would describe this line. So that's one problem, one type of thing that might show up in problems is that you might be given this kind of relationship and be told to swap the order, or maybe the problem forces it so that swapping the order would be easier to do. We don't really have any of that here because this is a simple polynomial to integrate. So we'll just do it in the order that is given to us, or the order that I've chosen to do. So doing dy first. Well, the integral with respect to y, that's pretty easy. Then you evaluate it, and that ends up being some messy algebra. I've tried to show my steps for doing the algebra, but uh, it's a bit of a bother, and certainly I would just prefer to use a calculator to simplify doing the algebra. But you end up with this point, at this point, if you simplify the algebra correctly. And then you integrate with respect to z. Okay, well that's not too bad. And notice it's the integral from 0 to 1. So a lot of these terms work out kind of nicely because they don't have a dependence on z. So when you integrate with respect to z, well, a z will pop out, and then the evaluation is going to evaluate z from 0 to 1. So that's just going to multiply by 1. So you see that this term stays the same because of that process. Same with the 15x, same with the negative 18. So the only things that do change are the terms that have z in them. So this becomes z squared over 2 that you would evaluate, which ends up just being 5x. This becomes 15 times z squared over 2, evaluate, is going to become minus 15 over 2. Okay, simplifying that a little further, we end up with this polynomial. And lastly, we integrate with respect to x, and I didn't bother to show the intermediate step of what you actually get when you integrate with respect to x, because everyone should be able to do that. It's just a polynomial. Evaluating gives you this quantity. Okay. All right, and is this the last? Yeah, this is the last example I have. Corresponds to your last problem. So in this example, you're given a triangular pyramid. It actually gives you a sketch of this thing, whereas I did not do so here. I only tell you that the solid E is bounded by this plane. I think it's pretty clear that you can see this is a plane, and so this is in the first octant. So what you can visualize from this is some plane that cuts through uh, the first octant in a diagonal kind of fashion, and it's going to then give you it's going to intersect the coordinate planes in such a way that it looks like this. And so you can hopefully see that this is a triangular pyramid. Okay. And the first thing that I do is I figure out what are my vertices of where does this plane intersect on the x, y, and z axes. So that's nice and easy to do because to intersect on one of these coordinate axes, you set the other two variables equal to 0 in this equation. So, for example, to intersect the z-axis, I would set x and y to 0, and I see that z is equal to 15. So this point is at z equals 15. That gives me this coordinate. To intersect the x-axis, I would set z and y equal to 0. So I have 15 is equal to, 0 is equal to 15 minus 3x. Move to the other side. I get that x is equal to 5. And similarly for the y-axis, if I set x and z to 0, we have 15 minus 5y equals 0. Move to the other side, divide. You get that y must be equal to 3. And so that's how we get these three coordinates. And then this last coordinate is just to describe this inner vertex here, this fourth vertex of the triangular pyramid, which we basically knew was there since it's described, the solid is described as being in the first octant. So we have this last point there at the origin. Okay. Now, if you remember your geometry formulas, then this problem doesn't require calculus at all. Right? We're asked to find the volume of a solid, the solid being a triangular pyramid. Well, the volume of a pyramid is 1/3 base times height, if you remember your geometry. So we can quickly plug things in, and I'm only doing this as just to have a way to double check our answer at the end, because the integration will be a lot messier, and so it's just nice to have something to check against. So 1/3 base times height. The base I'm using is the triangle in the xy plane. So it's 1/2 times 5 times 3, the legs of this right triangle there. Oh yeah, maybe I should comment that yes, all these triangles are right triangles. You can kind of tell that based on the way that this has been constructed. So that this forms the base, then you have 1/3, then you have the height in the z direction. And so this ends up calculating the volume of the pyramid, which ends up being 75/2 from geometry. Now, if we want to do this using integrals, we have to figure out how to sweep over this region. which is a little bit bothersome to do. But I've done a lot of problems involving this, and so I know how to work through this pretty quickly. So um, sometimes it can depend which triangle to project over, uh, like which projection to take as being easier. Here I've just chosen to do the integration over the xy plane first. So what you'll notice about this is, so x ranges from 0 to 5. And as you do that, you end up having a bunch of similar triangles. So maybe I can draw a similar triangle within this picture here, right? So this triangle in red should be similar to this triangle in the back in the YZ plane. And you can imagine that as you sweep along x, this triangle gets smaller or larger depending on which direction. And what's important here is that we're going to now try to describe um, how to sweep over the other variables, because you can see that once x is fixed, that changes the limits for how far you can go in the y direction and in the z direction, right? So all three of these variables are coupled with each other. Once we fix one of the outermost variables, the x, the y, or the z, the other two are going to end up depending on it. So I've just decided to fix x in this case. So let me draw a related picture to illustrate what's going on. I'm going to only write the x. I'm going to draw the xy plane. And so here we have x maxing out at 5, y maxing out at 3. And so this ends up being the triangle when we look at it top to bottom. Right. So this ends up being, I set this as being the outer region to integrate over, and then z is going to depend on the specific value x and y. So as you fix a particular value x, right? When you fix a particular value x, then you can see that the y ranges from 0 up to whatever this line is. And this line is maybe a little bit difficult to capture how to describe it, but it boils down to thinking about this guy actually. So what we're doing with this is we're setting, in this description, we're setting z equal to 0, and then we can move the variables to the other side. So you would have that 3x plus 5y is equal to 15, right? Since we're working only on the xy plane, we have z equals 0 in this case, and then we can move things to the other side. Now, once we fix a value for x, we can think of x as being a, I think the term is an independent variable, or is it dependent? It's the thing that y depends on. So I guess x is independent. So you could then solve for y. 15 minus 3x. So then y is equal to 15 minus 3x all over 5. So this is a description for this point that is on this diagonal line. And you can see that this is what I've written here. Y ranges from 0 to this upper expression. Okay. Then once you have both x and y, what you can do is rearrange this original equation, right? X and y are now treated as variables that z depends on. So x and y are independent variables. Z depends on them. And you can see that at maximum, z will hit this value. At minimum, z is going to be the value 0, right down here. But for a specific, do I have enough room here to pick a particular value? For a particular point there, you can see that z has that value as its maximum, which lies on this plane, this diagonal plane that is cutting out this pyramid. So the maximum occurs at this value, which is why I've written it here. So z ranges from 0 to this expression. Okay. Yeah, so that's how you do it if you want the ordering to be such that x is the innermost, y is the next, and then z is the outer. Or no, I reversed it. X is the outermost variable for that you integrate over, followed by y, followed by z as the innermost variable of integration. Right? You can see that because z ends up depending on x and y, z sits inside the integrals for x and y. If you wanted to use another integration order, you'd have to think about it. You'd have to change the directions that you're thinking about it in. Although if you set it up using like these kinds of equalities, and perhaps we could call them inequalities because they're sort of um, defining a region, a space, not just a line. But if you work with these kinds of inequalities, you solve for the other variable, you can end up getting all the other integration orders. So one thing to comment is that in previous runnings of this course, there was like an exercise that involved writing all 6 integration orders for these kinds of pyramids. And so from doing that, I got kind of experience with how you actually run through the process. But the process is really quite like this. You set some of them equal to 0 in order to figure out the range of one of them. And then once you fix one of the variables, you see how the other one depends um, on the range, or how the other one depends on the other variable. So just like what we did here, we first figured out how far x goes. Then when we pretend that x is some fixed quantity, we see how far y can go, right? So then in doing that, we would set z to 0. And then lastly, we have x and y as particular fixed constants, and we see how far z can go. And we end up with this kind of expression. So that whole process could be done for all of the integration orders. But we only need one in order to do this problem, and so I've just chosen this one. Okay. So feeding this information in, you can see we end up with this. This triple integral is calculating the volume. So similar to in like the two-dimensional case, when you integrate the function 1 over a region, that determines the area or the volume of the region. It depends on what dimension your region is. So if your region is two-dimensional, then integrating the function 1 over the region is going to measure the area. If you integrate over a three-dimensional region, the function 1 is going to give you the volume. And of course, if you integrate a one-dimensional region, it's going to give you the length. So it's just whatever the associated notion of area or volume is in the dimension you're working in. And you can see that I'm copying the bounds down. So x is the outermost guy with bounds from 0 to 5, followed by y with that fraction, followed by z with this that actually that was describing the plane that cuts out the pyramid. So this is the triple integral that will compute the volume of the solid. And then you go ahead and integrate this. Well, the innermost integral is easy because it's just 1. So integrating that is going to give you z evaluated from the lower function to the upper function. So that substitution just gives you this upper function. And then integrating this is with respect to y, well, it's a bunch of algebra. I think I tried to show some of the partial steps involved. So yeah, so when you integrate this, well, you have this term with both of these terms have y in front of them, which I've just decided to factor out. And then this guy, you get y squared over 2. Evaluate this from 15 minus 3x all over 5, and 0. So when you do that evaluation, a bit of simplification is involved. You get this kind of expression. And now this is all a function of x, so you can integrate with respect to x. Writing it in this form makes the integration a bit easier to, I guess, to compute by hand if you were to do it by hand. Since otherwise you'd have this as a polynomial, and the evaluation would be a bit more bothersome. Here, at least you can actually track what's going on. So when we integrate, we would get a, so this is one of those quick U subs, um, the mental U subs that you should hopefully be able to do by in your head. So you think of this whole thing as being a U because this is just a linear function. So this would be U cubed over 3. That gives you a 1 over 3. So that's, which I combine together. That gives me the 1 over 30. And then, well, to make the U happen, you'd have to um, multiply by 1, multiply and divide by negative 1/3. Um, how am I saying this? Um, you have to multiply and divide by negative 3. That keeps a negative 1/3 on the outside because the negative 3 is going to be absorbed as part of the u sub. The u sub requires a negative 3 because when you take the derivative of the inner function, you get negative 3. Um, so that allows us to do the mental u sub. It's going to just become this quantity, and then you'd evaluate this from 0 to 5. And when you do so, you end up with this result, which does match with what we got from geometry, so we should feel good about this process.